Hi, I'm Brett Andrews, an astronomy graduate student at The Ohio State University. Here I will present the main results from a paper titled Principal Component Abundance Analysis of Microlensed Bulge, Dwarf, and Subgiant Stars, written with David Weinberg, Jennifer Johnson, Thomas Bensby, and Sophia Feldstein. The formation and enrichment history of the galactic bulge is best traced by the abundance patterns of dwarf stars. Bulge dwarfs are normally faint, but microlensing can magnify them by a factor of 100, which has enabled Thomas Bensby and collaborators to determine well-measured abundances for up to 12 elements in 35 bulge dwarfs. We revisit this unique data set with Principal Component Abundance Analysis, or PCAA, a principal component analysis applied to the high-dimensional space defined by abundances. Often, the intrinsic variation in the data, that is, excluding variation due to noise, can be described by the first few principal components. For the bulge dwarfs, the intrinsic variation in the 12-dimensional abundance space is sufficiently described by 3 principal components. The first principal component, PC1, has strong contributions from the abundances of oxygen, other alpha elements, and aluminum, all products of type 2 supernovae. Iron is primarily synthesized in type 1a supernovae, so PC1 reflects the relative enrichment from type 2 and type 1a supernovae. PC2, the second principal component, captures the sodium-nickel correlation that results from metallicity-dependent type 2 supernova yields. A sodium-nickel correlation has been identified previously in halo stars, but this is the first time, to our knowledge, that a sodium-nickel correlation has been found in bulge stars. For comparison, we have done PCAA on a sample of local thin and thick disk dwarfs. The disk PC1 is nearly identical to the bulge PC1. The disk PC2, on the other hand, is almost exclusively correlated yttrium and barium, 2 elements chiefly produced in the S process of asymptotic giant branch stars. These stars live roughly a gig-a-year, much longer than the approximately 10 megayear lifetimes of the type 2 supernova progenitors that give rise to the sodium-nickel correlation in the bulge PC2. This discrepancy suggests that the bulge is formed more rapidly than the local disk. When we project bulge dwarfs in kinematically selected thin and thick disk dwarfs onto the bulge PC1, the bulge dwarfs form a bimodal distribution, analogous to the bimodality in iron abundance for these stars, and consistent with the bimodality seen in the thin and thick disk dwarfs. The metal-poor and alpha-rich bulge dwarfs correspond to the thick disk dwarfs, while the metal-rich and alpha-poor bulge dwarfs coincide with the thin disk dwarfs. This agreement hints that secular processes may have heated inner disk stars to form the bulge, although other formation mechanisms could have created similar results. Stars with unusual abundance patterns, due to their origin in an accreted satellite galaxy or their enrichment by a rare and interesting nucleosynthetic process, can be identified by the location in principal component space or through chi-squared fitting of the first few principal components to the abundances of a star. We have shown that PCAA is a powerful technique for analyzing highly dimensional datasets, such as those to be created by current and upcoming surveys like Apogee, Gaia ESO, and Hermes.